Mama, I need a break. I've been working very hard for my exam.
Break? But in terms of science, the activities that you have been involved in do not involve work at all.
That's not fair. I've been studying for quite some time now.
That's true. But do you know what exactly work means in physics?
Not exactly.
In this lesson, you will learn about work. At the end of this lesson, you will be able to explain the concept of work, state the two conditions that need to be satisfied for work to be done, define work in a scenario where a constant force is acting in the direction of displacement, and define positive and negative work. To understand the concept of work, let's look into some situations. A woman at a mall pushes a trolley and moves the trolley through a certain distance. Jerry tries very hard to push a huge boulder, but the boulder does not move. A man tries very hard to pull a fallen tree trunk tied forward with a rope. However, the tree trunk does not move. A man pulls a hand cart through a distance of 500 meters. In the given situations, all the four characters have applied force. But the result of that force differs. The woman and the handcart puller are able to move the trolley and the handcart across a certain distance. However, Jerry doesn't have much success in moving the boulder, and the man is not able to move the fallen tree. In scientific terms, the woman pushing the trolley and the man pulling the handcart performed some work. However, the man trying to pull the fallen tree and Jerry have not done any work.
Oh, I see. That's why you said I haven't done any work. I haven't actually been involved in moving any objects.
That's right. Work done by force acting on an object is equal to the magnitude of the force multiplied by the distance moved by the object in the direction of the force. That is, displacement of the object. Looking at the definition of work, for any work to be done, first a force has to be applied on the object in order to displace the object from its initial position. The initial position of an object could be the position of rest. Therefore, the two conditions that need to be satisfied to say that work is done are: a net force should act on an object. The object must be displaced in the direction of the net force. Now let's check how clear your understanding is about the concept of work. Consider three cases: a book lying on the table, a horse pulling a cart through a certain distance, a man trying to push a huge rock. Can you tell me in which of these cases work is done?
In the first case, where the book lies on the table, no work is done, as we have not applied any force. This implies that the force applied is zero. Hence, the work done is zero. In the second case, the horse applies force to pull the cart across a certain distance. As there is displacement of the cart in the direction of the force, we can say that work has been done. Finally, in the third case, the man applies force to move the rock, but clearly the force is not enough to move the rock. Since there is no displacement in the rock's position, no work is done. Is that right?
Absolutely. That's very good. So, let us now look at defining work. Work is said to be done when a certain amount of force is applied on an object. This force displaces the object through a certain distance s in the direction of the force. Scenarios involving work may be of two types. The first is where the force is acting in the direction of displacement. The second type, where the force is acting in a direction opposite to that of displacement. That is, one of the identified forces F is acting in a direction opposite to the direction of the displacement S. Thus, the angle between the two directions is 180 degrees. Let the work done be W, the force acting on an object be F, and the displacement of the object be S. The work done is the product of force and displacement. Thus, the work done by the net force acting on an object equals the magnitude of the net force multiplied by the displacement of the object in the direction of the force. The unit of work is the product of the unit of force and the unit of displacement. In the SI system, unit of force is expressed in Newton and the unit of displacement is expressed in meters. Therefore, the unit of work is Newton meter. In the honor of scientist James Presford Joule, 1 Newton meter is referred to as joule, denoted by the letter J. Thus, 1 joule is defined as the work done when the net force of 1 Newton acts on a body and displaces it in the direction of the force by 1 meter. In the Cbse system, the unit of force is dyne, denoted by dyn, and the unit of displacement is centimeter, denoted by cm. Therefore, the Cbse unit of work is dyne centimeter. 1 dyne centimeter is referred to as erg. Thus, 1 erg is defined as the work done when a net force of 1 dyne acts on a body and displaces it in the direction of the force by 1 centimeter.
Are joule and erg related then?
Sure they are. Let's determine how exactly they are related. A force of 1 Newton is equal to 10 raised to the power 5 dyne. A displacement of 1 meter is equal to 100 centimeters. Thus, the work of 1 joule is equal to the product of 10 raised to the power 5 dyne and 100 centimeters. This is equal to 10 raised to the power 7 dyne centimeters, as 1 dyne centimeter is equal to 1 erg. We get 1 joule is equal to 10 raised to the power 7 erg.
What about the path followed by an object regarding the calculation of the work done on it? Doesn't that affect the work done in some way?
Not really. Consider an object displaced from the point A to the point B on the application of a constant force F. The object can be displaced from A to B in any of the paths, that is, P1, P2 or P3. But the displacement of the object still remains the same, that is, S, the shortest path from A to B. Work is equal to the product of force and displacement. As you can see, force and displacement are constant regardless of the path the object traverses. Thus, the work done on the object is independent of the path traversed by the object. It depends only on the initial and final positions of the object. Let me summarize what we have been talking about. To describe work done on an object, we require the magnitude of the net force acting on the object, its initial position, and its final position. We do not require the direction of motion of the object. Thus, work is a scalar quantity. Now, I'd like you to consider two cases. In the first case, a force of 100 Newton displaces a block A on a smooth floor through 5 meters by pushing it horizontally. And in the second case, a force of 25 Newton displaces a block B on a smooth floor through 20 meters by pulling it horizontally. Can you tell me in which case more work has been done?
Let me see. Even though the force applied and the displacement of the blocks in both the cases is different, the product of the force applied on the blocks and their displacement seems to be the same. Work done on the block A is the product of 100 Newton and 5 meters, which is equal to 500 joule. Work done on block B is equal to 25 Newton multiplied by 20 meters, which is equal to 500 joule. That means that the work done in both these cases is the same.
Correct. Very good. Now we have learned to examine situations to determine whether or not work is done in a specific situation. However, the interesting thing about work is that it can be positive as well as negative.
Really? How is that?
Let me explain through some examples. First, consider two situations where force and displacement are in the same direction. Case 1. A boy shifts a table from one spot to another in a room. He does this by pushing it over the smooth floor of the room. Case 2. A small child pulls a toy cart with rubber wheels over a smooth floor. In both the cases, some work is done and the force and displacement are in the same direction. Where both the force and the displacement are in the same direction, the work done is called positive work.
What about negative work?
I'm coming to that. Let us consider two more cases. Case 1. A porter pushes a wooden block on a rough surface. Here, the porter applies force on the block in the forward direction. This force does positive work since the direction of the applied force is the same as that of the displacement of the block. However, the frictional force on the block does negative work since the direction of the frictional force on the block is opposite to that of the displacement of the block. Case 2. A stout person is walking. A lean man tries to stop him. The stout man overcomes the force applied by the lean man and continues to walk, but he is walking slower than before. Here, the direction of the force applied on the stout person is opposite to that of his displacement. Thus, the work done on the stout person by the lean person is negative. So we can say that when the force acts in a direction opposite to the direction of displacement, the work done is negative. In such situations, the work done by the force F is taken as negative and denoted by the minus sign. The work done by the force is the product of F and minus S, or the product of minus F and S.
Okay, I think I got it.
This brings us to the end of this lesson on work. In this lesson, you learned what work means in terms of signs. You also learned to distinguish between positive and negative work, as well as calculate work done. The section on solved problems provides you an opportunity to review some model problems based on these concepts. To revisit the key points covered in this lesson, please review the flashcard at the end of this lesson.
Can we go home now?
We'll have to wait a bit. We need solar energy to charge our batteries. The ship won't work without it.
Power bite is the secret of my energy.
Wow! That was a lot of work. Looks like energy and work go hand in hand, doesn't it? In this lesson, you learn about energy. At the end of this lesson, you will be able to identify the relationship between work and energy. Identify the various forms of energy, including potential, kinetic, electrical, thermal, chemical, and solar energy. Explain potential energy. Define gravitational potential energy. Derive the expression for gravitational potential energy. Define kinetic energy. Derive the expression for kinetic energy. Explain how energy gets converted from one form to another. Explain the law of conservation of energy. Define power. And identify the significance of commercial unit of energy.
It looks like nothing works without energy.
That's true. In fact, the word energy is derived from the Greek word energia, meaning at work or in work. Thus, energy is defined as the capacity to do work.
But how exactly do objects use energy to do work?
Well, it's like this. The object which does the work loses energy, and the object on which the work is done gains energy. Consider a spring and a ball. The spring is compressed and placed behind the ball. When the spring is released, it pushes the ball forward. The spring loses its energy and the ball gains energy. In other words, an object that possesses energy can do work on another object. When this happens, energy is transferred from the former to the latter. The second object may move as it receives energy.
Oh, so work is basically a transfer of energy. So how about the unit of energy?
Good thinking. The unit of energy is the same as that of work. Thus, the unit of energy in the SI system is joule, and in the Cgs system, erg. Like work, energy is also a scalar physical quantity. You can find energy in different forms. Energy of an object due to its position or arrangement in a system is called potential energy. For example, the work done in winding the key of a toy car is stored in the form of potential energy in it. This energy is released as the spring unwinds and sets the car in motion when it is left free on the floor. Further, consider the bow and arrow system. When the bow is stretched, the arrow gains potential energy. Another example is of water in a reservoir. This water has potential energy. This potential energy converts to another form of energy called kinetic energy when the water is released and can work to generate electricity. And that brings us to electrical energy, something without which we would find it difficult to work and perform simple tasks. This energy enables the functioning of various electrical appliances and machines such as refrigerators, televisions, computers, and much more. Now, observe this boy kicking a ball. This ball moved with energy called kinetic energy. The energy possessed by a moving object is kinetic energy. Another form of energy that we take for granted in our daily lives is light. The energy that gives us the sensation of vision is light energy.
But how is light energy used to do work?
Well, light is a major component of the solar energy that we receive from the sun. For a more direct example, think of photosynthesis, a process where light energy is used by the plants to make food. Thermal energy or heat energy is the energy that gives us the sensation of heat. For instance, heat energy produced from the flames in a gas stove helps cook food.
Oh, power cut. Let me find my torch. Another form of energy, light energy.
Actually, light energy produced by the torch is a result of the chemical energy stored in the battery. Chemical energy is a part of the energy released during a chemical reaction in the battery. In this lesson, we will focus on potential energy and kinetic energy. As mentioned earlier, energy stored in an object due to its position or arrangement in a system is known as potential energy. Observe the child winding a key in the toy car. The key is actually connected to a spring. Potential energy is stored in the toy by the winding of the spring in the toy by the child. This spring, when released, enables the toy to move. That's how the toy is set in motion when put back on the floor after winding.
So every object that's above ground level has some potential energy?
That's right. When an object is at a certain height from the ground or any reference level, it is said to possess potential energy. This energy is called gravitational potential energy. This energy is the work done in raising an object from the ground to a certain point against gravity. Look at these two objects. A book on a table and a book on the top shelf of a cupboard. Which of these do you think has a higher potential energy?
I would say the book on the top shelf of the cupboard.
Correct. The higher the object is raised, the more is the gravitational potential energy stored in it. That's why a rock resting on the edge of a cliff high above the ground possesses high gravitational potential energy in comparison to the other objects which are relatively at a lower height than the cliff.
But how would I know how much gravitational potential energy an object has?
We can derive an expression for it. Consider an object being lifted to a height h from ground level. Potential energy stored in the object is equal to the work done on the object. Further, the work done upon the object is equal to the product of applied force and the displacement caused. We can determine the displacement of the object by measuring the height through which it has been lifted. Now let's determine the applied force on the object. In this case, the applied force on the object equals the weight of the object. The weight of an object is equal to the product of the mass of the object and the acceleration due to gravity. Hence, gravitational potential energy of an object is the product of its mass, its acceleration due to gravity, and the height through which it is raised.
Raised from what? Does height always refer to height from the ground?
That's a good question. To calculate the gravitational potential energy of an object, it is important to get the reference level right. Let's consider 4 cases to understand the gravitational potential energy of an object with respect to different reference levels. Case 1. Consider a wooden block of mass 10 kilograms placed on the surface of a table of height 2 meters. If acceleration due to gravity is 9.8 meters per second squared, then the gravitational potential energy of the block with respect to the floor is the product of its mass, acceleration due to gravity, and its height from the floor. Calculations show that the gravitational potential energy of the block is 196 joule. As you can see, these calculations determine the gravitational potential energy of the block with respect to the floor. Hence, here, the floor is the reference level. Now let's consider case 2, where a stool that is half a meter tall is placed beside the table. The potential energy of the block with respect to the stool is the product of its mass, acceleration due to gravity, and the difference between the height of the table and the stool. That is 147 joule. Here, the surface of the stool is the reference level for the calculation for the gravitational potential energy.
Can there be a case where the gravitational potential energy of the block on the table is 0?
That's what I was coming to. In the third case, if the reference level of the block is taken as the surface of the table itself, then the height of the block is 0. In such a case, its potential energy is 0. Generally, the surface of the earth is taken as the reference to determine the height of an object.
That's interesting. But I have another question. From the examples we have seen so far, gravitational potential energy always seems to be positive or 0. Is it possible for the block to have negative gravitational potential energy?
Yes. Case 4 illustrates such a situation. Suppose the block is placed on the surface of the stool. In such a situation, if we take the reference level of the block as the surface of the table, then the potential energy of the block is negative. As you can observe, the value of the height of the block with respect to the table is the same as that in the second case, which is 1.5 meter. Even the value of acceleration due to gravity and mass of the block remains constant. The difference in this case is that the height of the block is measured downwards. Unlike the first 2 cases, where the height of the block is measured in the upward direction. When height is measured in the upward direction, it is considered positive. However, when measured in the downward direction, height is considered negative. We can obtain the value of gravitational potential energy of the block, in this case by substituting the values of mass, acceleration due to gravity, and height of the block in the expression PE is equal to mgh. The height in this case being negative, the gravitational potential energy of the block in this case is minus 147 joule. We just learnt about potential energy in objects with reference to a specific level. But what happens when these objects are moved? For example, when a coconut drops from a tree onto wet sand.
Well, I can see a depression where the coconut dropped on the sand.
True. In motion, the coconut does some work because it now has energy due to movement. The energy possessed in a moving object is called kinetic energy. Now let's see what happens if we again drop the coconut from a lesser height, say 1 meter.
It still makes a depression on the sand. But this depression is not as deep as the one made earlier by the coconut that dropped from the tree.
That's because the first time the coconut was dropped from a greater height and hence had higher speed. This gave it more energy to do work. Thus, more work was done when the distance travelled by the coconut was more.
Okay, so, like potential energy, there must be a formula for calculating kinetic energy.
Yes. Let's derive the formula to calculate kinetic energy of a moving object. Consider an object of mass m, initially at rest. Thus, its velocity initially u is 0. Let us assume that a constant net force F acts on the body for t seconds and brings it to motion in the direction of the force. At the end of t seconds, let v be its velocity, s be its displacement during the interval t, and a be the acceleration produced in the body. Amount of work done is the product of force applied and the displacement caused by the applied force in the direction of the force. According to Newton's second law of motion, force is mass times the acceleration in the body. This makes the work done equal to the product of mass, acceleration, and displacement. Let this be equation 1. According to equations of motion, for a body in linear motion, the relation between initial velocity u, final velocity v, acceleration a, and the displacement of a body s is given as v square is equal to u square plus twice the product of a and s. Thus, acceleration a is equal to v square minus u square divided by twice s. Let this be equation 2. Substituting equation 2 in equation 1, we get the work done as half of mass m multiplied by the difference of v square and u square. As the final velocity v of the body is greater than its initial velocity u, the work done is equal to the change in its kinetic energy. However, the initial velocity of the body is 0. Therefore, we get kinetic energy as half the product of mass and velocity squared.
You said the work was done by kinetic energy. But then, what happened to the potential energy of the coconut when it dropped down?
The potential energy got converted to kinetic energy as the coconut gained velocity during its fall. In fact, conversion of energy from one form to another is a very common phenomenon observed in our daily life. For example, in a microwave oven, the electrical energy is converted into thermal or heat energy. This heat produced in the oven enables us to bake food in the oven. An electric bulb is another example where electrical energy is converted into light energy, as well as heat energy.
What about a fan?
In a fan, electrical energy is converted into mechanical energy. Another interesting example of conversion of energy is a catapult. When you stretch the catapult with a stone in it the stone gains potential energy due to the stretch of the elastic bands of the catapult. Once the stone is released from the catapult, the potential energy of the stone is converted into kinetic energy. With this energy, it can hit a target. And finally, the colorful displays from firecrackers also involve conversion of energy. When we ignite a firecracker, the chemical energy stored in the cracker results in producing the sound, light, and heat effects that you see. A good way to understand conversion of energy is to examine how electricity is produced in a hydroelectric dam. The stored water in the reservoir of the dam possesses potential energy. When the stored water of the dam is released into the turbine through the penstock, the potential energy of the water is converted into kinetic energy. This flowing water rotates the blades of the turbine, which is the mechanical energy. These rotating blades of the turbine produce the electrical energy.
So, basically, energy gets converted from one form to another. Doesn't it ever get used up?
No. Just like momentum and mass, energy in a system is constant. The law of conservation of energy states that energy can neither be created nor destroyed, but can change its form. An example will help you understand this law better. Let a body of mass m be released from a height h above the ground. We can regard the point from which the body was released as point A. At this point, since the body is at rest, the potential energy is equal to the product of mass, acceleration due to gravity, and the height. The velocity of the body is 0, making kinetic energy also equal to 0. Hence, at A, the total energy is equal to the product of mass, acceleration due to gravity, and height. Let this denote equation 1. When the body is falling down, consider a point B at a distance x from A, the initial rest position. Here, the height of body becomes the difference between h and x, and we get the potential energy as mg multiplied by h minus x. At point B, the body has covered a distance x. Its velocity at the end of this distance is v. The kinetic energy of the body at B is equal to half mv square. The total energy E at B is the sum of potential and kinetic energies at B. That is, it is the sum of mg multiplied by h minus x and half mv square. Let this be equation 2. To get the final velocity of the body at B, you need to apply the equation of motion related to displacement, initial velocity, final velocity, and acceleration. Here, the initial velocity u is 0. The acceleration of a free-falling body is only due to gravity. Substituting the corresponding variables in the expression for final velocity and simplifying, you get the square of the final velocity of the body at B equals 2gx. Let this be equation 3. Substituting equation 3 in equation 2 and simplifying, the total energy at B equals mgh. Thus, the total energy at B is again equal to the total energy at A. Let this denote equation 4. When the body reaches the ground at point C, the potential energy is 0, since the height of this body from the ground is 0. At this point, the body has covered a distance h from its initial position A. Let the velocity of the body at C be v. Its kinetic energy at C is equal to half mv square. The total energy E at C is the sum of the potential and kinetic energies at C. That is, the sum of 0 and half mv square. Let this be equation 5. To get the final velocity of the body at B, you need to apply the equation of motion related to displacement, initial velocity, final velocity, and acceleration. Here, the initial velocity u is 0 at A. The acceleration of a free-falling body is only due to gravity. By substituting the corresponding variables in the expression for final velocity and simplifying, you get square of the final velocity of the body at B as 2gh. Let this be equation 6. Substituting equation 6 in equation 5 and simplifying, you get the total energy at C equals mgh. Thus, the total energy at C is again equal to the total energy at A. Let this denote equation 7. Now compare equations 1, 4 and 7. As you can see, the expression on the right-hand side of all three equations is identical. That is, the total energy of the body is the same at all times. Therefore, by comparing these three equations, we can infer that the total energy in the object remains constant at all times. This shows that the law of conservation of energy holds well in the case of a free-falling body. Let's look at another aspect of energy used to do work, the rate of doing work. Consider these two weightlifters who are of the same height and will be lifting up equal weights.
The first weightlifter is struggling with the weight, but the second one seems to have no problems.
So, you notice that even though both the men are of the same height, one was able to lift the weight quickly, while the other struggled with it. What do you think is the reason for this difference?
Well, the second weightlifter looks stronger.
Yes, in terms of science, you could say he has more power to do the work. Power is defined as the rate of doing work. It is a measure of how fast a given work is done. The greater the power of a body, the more is the work done by it in a given time. Based on its definition, power is the rate at which work is done. That is, the amount of work done per unit time. Work done is applied force times the displacement caused due to the force. Thus, power can be expressed as the ratio of product of force and displacement to time. Since power is the ratio of work done to the time taken, unit of power is unit of work divided by unit of time. In SI system, unit of work is Newton meter and unit of time is second. Thus, the unit of power in SI system is Newton meter per second. 1 Newton meter is 1 joule. This gives the SI unit of power as joule per second, which is watt. In the Cbse system, power is measured in erg per second.
The power is back. I just realized we always refer to electrical energy as power. Why is that?
That's a good question. Power is the ratio of energy consumed to the time taken. Thus, energy can also be expressed as the product of power and time.
So, how do we measure the electricity that we use? Is it in joule?
The unit joule is too small to express large quantities of energy. For convenience, we use a bigger unit of energy, kilowatt hour, denoted by kWh. Let us say we have a machine that uses 1000 joule of energy every second. If this machine is used continuously for 1 hour, it will consume 1 kilowatt hour of energy.
Let me see. So, 1 kilowatt hour is the energy used in 1 hour at the rate of 1000 joule per second.
That's very good. Further, 3600 seconds make an hour. Thus, 1 kilowatt hour is equivalent to 3.6 multiplied by 10 raised to the power 6 joule. This brings you to the end of this lesson on energy. In this lesson, you learned about the significance of energy, various types of energy, and how to calculate the energy of an object. The section on solved problems provides you an opportunity to review some model problems based on these concepts. To revisit the key points covered in this lesson, please review the flashcard.